And I've been asked to talk about these new theories of deformation in amorphous solids. I'd like to give a talk, sort of a summary talk. What I'd like to do is because this field has been going on for some years now, ever since Mike Falk got it started with some help from me, and it's evolved. It looks to me as if it's going in the right direction, but among other things I'm thinking about now is that it's time to rethink where we are and what we're doing and what the purposes of it are. Here's a list of things I'd like to talk about, and it's obviously much too long. And are you getting it? So what I'd like to try to cover in the time available is to emphasize this question about where are we, what do we really know, where are we on and where are we off track in trying to figure out how to make a theory of deformation and failure in amorphous materials. So I'd like to spend some time talking about the main objective of the STZ shear transformation theory, and emphasize something about the basic assumptions rather than put in a lot of detail. I'll summarize the zero temperature theory and the finite temperature theory because I want to get to the place where I can at least show you that there is some sensible, at least in the last couple of years, way of comparing with some experimental data. It's not all the way there yet. I'd love to be able to talk about shear banding because the effective temperature idea brings in a whole new dimension about how one can understand shear banding, but I don't think I'm going to have time to do that. I'd love to talk about some of the new ideas on how you make a first principles theory of the super Arrhenius transition rates, and maybe I'll be able to say a few words about that. And then there's another exceedingly interesting puzzle that has been emphasized by Bill Johnson recently, mostly privately to me, about the possibility that there are some really universal features in this whole field, that after all, an amorphous solid looks an awful lot like a liquid, looks like again, a whole variety of glasses. There ought to be simple ways of describing these things, sort of fundamental ways of describing these things that relate to a whole bunch of the stuff, including perhaps even granular materials. And we're not there yet, but this is an interesting clue about why we might get there. And I don't think I'm going to have time to talk about that either. But let's see. So the main objective. What's the main objective of this kind of theoretical work? Well, look, I think what we're obliged to try to do is to close a gap between fundamental theoretical physicists, natural philosophers, and engineers who, I believe, try to design, form materials or predict the behaviors of materials, especially predict the way that materials are going to fail in practice. I don't think, I've become very opinionated about these questions in recent years. I don't think we've done a good job of doing that. I think it's largely the failure of the theorists. You could sort of blame experimentalists because they've not produced experimental data that can really probe interesting questions, but I think the theorists have failed to ask the questions. And so I think that's what we need to do, is to ask the right questions that will allow us to produce a theory of this sort of wide range of materials, amorphous solids, but foam, suspension, perhaps even granular materials, so that we can describe their behaviors in a way that's predictive. And that's what I think the main objective of this kind of work really ought to be at this stage of the game. And needless to say, as you do it, you're going to find more and more fundamental questions that tickle the imagination of people that live at the KITP. But that's the name of the game. So what are we aiming for? I think it's, roughly speaking, the analog of Navier-Stokes equations. Sort of a semi-phenomenological but firmly grounded way of describing the behaviors of these systems that is at least as tractable and as useful as Navier-Stokes equations are for fluids. And after all, as I said already, amorphous materials aren't that far from being fluids. They're different in some very interesting ways, but it ought to be possible. So, how do I put that? This is the most complicated mathematical slide I'm going to show you. How do I put that in a context? That if I want to make a continuum theory of large-scale deformations, I want to therefore, but I want to do it in a solid. So I've got to start with, this is the mass times acceleration equation, oh, good. I was looking around for that and I didn't see it. So I've got to start with F equals ma, just the way you do for hydrodynamics. Then in a solid, I have to do this stuff in tensor version, so I've got to write a rate of deformation tensor. And this is already a bit of an assumption. I'm going to separate it into elastic and plastic parts. But I'm going to be very careful when I write curly d by dt. I mean both advection and rotation. That's the kind of stuff, that's the reason that we physicists don't like dealing with solids, is that you have to do things like that. You have to do it. It's a sort of a technical extra stuff. And then the guts of what I'm going to talk about today sits here, is that I need the plastic part. Sometimes I'll call it the plastic strain rate. But technically it's the plastic part of the rate of deformation tensor. And that's where constitutive equations have to come in. And so we have to try to develop the constitutive equations that come into this part. And then, if you've got all this put together, then you could start solving problems like the necking in bars that was on the frontispiece of the, and I'll show you some other pictures similar to that. So here's one of Lance Eastgate's rather rudimentary numerical simulations. These are solutions of an STZ equations. He's doing essentially the same experiment as you do when you do a necking kind of experiment, where you hold these edges fixed of a sample, you have some roughness along these edges, and you pull or you push, and you look to see how this free surface develops. And you also look, you see what Lance is plotting here is, it's essentially the STZ activity, or it's the rate of dissipation, and you can see that, in fact, what he's getting are some nascent shear bands that occur in there already, although there's no shear banding instability in these equations that I know of, except for the way they may couple to the motions of the boundaries. This was designed as the analog of one of Mike Falk's recent molecular dynamics simulations, relatively recent in the last few years. And this is in fact going to be the leitmotif for almost everything I'm going to say, because I'm going to show this picture in a variety of different guises. What Michael has done here is he's done exactly the same experiment. He's held this boundary and that boundary fixed. There's some these are free boundaries, and they necessarily have some intrinsic roughness to them. This is a molecular dynamics simulation, two-dimensional Leonard-Jones interactions. It's an amorphous material. And the dark blue stuff is the shear transformation zone activity. I'm going to define that a little bit better before, but that, roughly speaking, that identifies the places where there are irreversible rearrangements of the atoms in this material. And again, you see that there's a a shear band that seems to be developing along there. So that's a sort of a computer experiment. We have then rudimentary STZ theoretical calculations that go along with it.
And during these rearrangements, there is a conversion of elastic strain to plastic strain?
Yeah, precisely. In fact, we'll talk about that. Here's another one of Michael's by now classic pictures, which shows exactly where that rearrangement is occurring. So that's, but the important point that I wanted to emphasize on this slide is that I'm going to take here what is the traditional engineering point of view, which is different from the traditional physicists or chemical physicists or point of view, where people would like to start with a liquid description of a system, do things like mode coupling theories, and try to understand how the atoms interact in the liquid, and as you go down in temperature or up in density, the liquid gets more and more viscous and somehow becomes a glass. That's a very interesting way of looking at it. It has had some significant progress, but I think it has not managed to make quite the contact that we need yet for the fundamental purposes that I was trying to propose. I think it's one of the really interesting theoretical challenges is to bridge the gap between the liquid-like and the solid-like description. Here I'm going to start with a solid-like description. I'm going to assume, like Turnbull and Cohen and Ali Argonne and Franz Papen and generations of people in the engineering literature, that we have basically a solid, an amorphous solid, but it has elasticity and it behaves in all sorts of ways like a solid. But inside that solid are zones that are somehow soft. Originally these were called flow defects or shear transformation zones. And they are places where, for some reason or other, the atoms have a relatively loose configuration. And here we've identified the 4 atoms, 1 big one and 3 little ones, with an oval. And then this material is undergoing pure shear. And so there's a rearrangement that occurs here. Instead of these being nearest neighbors, now this and the big one are nearest neighbors. So you see that happening in there. And then there are other similar things happening in that region, actually at different times. This is a slightly misleading picture, but it's the best one Michael has given me for the last 10 years that shows precisely this point. So it's a localized event, and that's where the irreversible rearrangements occur, and that's what contributes to the plastic deformation of the system. And everybody else around here is basically elastic. Now, one very important idea here is that these STZs, unlike in many models of them, they don't diffuse. They're stuck at certain positions. They may, of course, move with the material. That's a different thing. They may disappear, or they may be created, but they are not mobile defects. And that distinguishes this approach from a number of others. Well, what's the STZ model? What we're going to say is that those defects are two-state systems. They can exist this way or that way. I'll make a better picture of this in the next slide. They can be at angles, but that's different. That's the same thing. And the idea is that the populations of these defects, the number of them, and also their orientations, which is very important, are going to determine and what the response of the system is going to be when I apply forces to it. Very important reason for making these two-state systems, for including the internal degrees of freedom there, which has been, again, it's missing in previous versions of these theories, namely that that's the way you can see that these materials have memory effects. That's how they can, how they remember whether they've been sheared this way or that way, and therefore respond accordingly to the next shearing or deformation event. We know experimentally that that happens. Within a theory like this, if we're going to keep those memory effects, we have to have some internal degree of freedom, like this orientation of these defects, that is going to remember and, by the way, very importantly, forget over time what the previous history of deformation was. And finally, and I shouldn't have to mention this, but the history of the subject is replete with theories that violate the second law of thermodynamics, or violate mirror symmetry, or even do worse things. The mathematical literature is full of stuff that you don't even want to hear about. I could tell you a Jim Rice story about that from a few years ago. When I fussed about this, and Jim said, "Oh, we've known that for 30 years," and pointed out he had it in his papers, and I said, "Well, how come they're still publishing textbooks and review articles that have the wrong kinds of internal variables in them?" And he said, "Oh, we just don't pay attention to that." For which among the many things for which I'm eternally grateful for Jim, is that so I just erased all that stuff from the papers that I was writing. All right, now we have to turn this into into some bit of mathematics, and here I'm basically just repeating Mike Falk's PhD thesis, and it was Mike Falk's idea. And so here's this caricature of this two-state system where it can be elongated this way or elongated that way, and it can make transitions back and forth between the two of them. So the fundamental quantities in the theory is the populations of these zones. And we call them n plus and n minus here. And then the plastic strain rate is just the rate at which these things go this way minus the rate at which they go that way. Okay, that's easy. Then we have to write an equation of motion, a sort of master equation for these populations. And that's also easy. Obviously, if I have things going forward, I deplete the minus ones, etc. So this part, which looks just like the strain rate. But then there's an extra part, the Falk term, that says, well, I can annihilate and create them. And so the first term here is the rate at which I'm creating new zones. And the second term is the rate at which I'm annihilating them. Okay? And then there's this interesting quantity gamma that sits there. And that's been the source of a whole lot of confusion in the literature. And the question is, well, what is gamma? Well, I'm going to come back to what gamma is, but first I just have to introduce a little bit of notation that I'll call n plus plus n minus normalized by some number. Capital lambda, it's a dimensionless density of the zones. And then there's a quantity which is the difference between the n minus and n plus. And that's the orientational bias. And when I go to a fully 2 or 3 dimensional continuum theory, it's this quantity. See, that one's going to remain a scalar, the density, but this quantity is going to become an important tensor. And I'm not going to talk about exactly how it does that, but it's sort of obvious that it has to be. And so the two crucial variables are lambda and delta. Those are going to be the internal state variables that are going to carry the memory of what's going on, and especially the delta. Because now,
so lambda starts its life as 1?
No, lambda starts its life it's an important question. Lambda starts its life depending upon how the sample was prepared. It'll only be one, and
so n infinity then is not the initial.
No, n infinity is just a reference density that it's going to come into some Boltzmann factor eventually. Then I have got to figure out what. I'm sorry, I jumped a slide. I just was showing this equation again. That's the same one that was on before, but the only new point is that I'm now being explicit that gamma has to be a function of these internal variables, these state variables, as well as the stress. That's the annihilation and creation rate. But then it's Pechenek's idea. I never get any of these ideas myself these days. It's true. If you simply notice that what really ought to determine the rate at which I'm stirring up the system is the rate at which I'm dissipating energy. After all, I'm shearing it with some external force. I do the first law of thermodynamics that says that part of that energy is stored in internal energy, but part of it is dissipated. What Michael and I at first thought was that gamma should be just the rate at which I was doing work on it, but that has some real problems. It can change sign in particular, and this has to be a positive number, and if you let it change sign, you really get into a mess. You have to. So what Leonid noticed was, okay, we'll make it equal to not the rate at which I'm doing work on the system, it's the rate at which the system is dissipating the energy. By the second law of thermodynamics, that is a necessarily positive quantity. And then what Leonid noticed was that that's all you need. Is you put that into the equations of motion, and insist that it satisfy the second law of thermodynamics. It gives you a unique expression for gamma as a function of S and lambda and delta. And in particular, the way it looks, roughly speaking, is that it's sort of like the strain rate squared, which is a nice positive number, but it's got this extra denominator on it, which in fact, when you then work through the equations of motion, produces all kinds of extra simplicities and internal consistencies and dynamical stuff, which, again, among other things, I don't have time to get into.
So you start out with gamma being equal or proportional to the energy dissipation?
Well, in fact, it turns out that under most circumstances, it's just equal. I originally thought, and in fact, even in Leonid's papers, and he plays around with the possibility that there's an extra proportionality constant there. But you can get yourself into trouble with that. There's no reason why it shouldn't be just equal to. What? Yeah. It's first place. It's the energy dissipation rate per STZ that has to come in there. This is where it gets only slightly technical, but it turns out you really have very little wiggle room when you do this.
Is it absolutely crucial that this gamma depends on lambda and delta, making theory linear in the sense of...
Oh, it's a very nonlinear theory. Oh, yeah, it has to.
So this theory doesn't exist if gamma depends only on S.
No, it wouldn't work. It wouldn't work. Look, the traditional Spapen-Argon assumption was that gamma was just equal to the strain rate itself, which has real problems if you think about it. So, what comes out of this, and now I'm just going to describe this in words rather than try to do equations. You get equations of motion for lambda and delta, and that just comes from the n plus minus equation. And you have to put in various physical models of the rate function R of S, but we play with that a lot. Basically, the idea is to put in a rate function that has as few parameters as possible, and that works. What?
Why is important that gamma is function of lambda and delta, and R is not always?
Well, R is a sort of given ingredient. That comes directly from the physics. It's a question of how I'm straining it. It's going to be some sort of a activation factor, or maybe it's got something having to do with the rate at which friction drives greens across each other. There's physics in there, and basically you shouldn't have any control of that. Whereas gamma should be a derived quantity. Okay?
It must presume that the density is relatively low to the different zones. So
well, that's right. And in fact, we've played around with theories in which they do. And as a matter of fact, already in these theories, the zones will influence each other because they'll set up stress fields and things like that. I'll show you that. Now, the main result of this analysis, though, is that automatically a yield stress comes out. It comes out because the equations of motion exhibit an exchange of dynamic stability. That at low stresses, the jammed state, where the shear rate, plastic strain rate vanishes, that's the only stable state of the system, at least for a uniform system. Whereas at higher stresses, the only stable state of the system is one in which it's flowing. And there's a point at which there's an exchange of stability between these two steady states, and that is obviously what you want to identify as the yield stress. So that's one of the neat things about this, is that a yield stress automatically emerges. Now, granted, it's sensitive to what properties you've chosen for the R of S, and you can, if you know what you're doing, you can build a yield stress into that. But you can also put something in there that doesn't look as if it has a yield stress at all, and all of a sudden the yield stress drops out. Now, so what I just said, here's a characteristic diagram. If I'd been cleverer, I would have had this curving a little bit. Maybe I'll try to do that. But the point is that this is strain rate, this is stress, and at strain, there's the jam states up to some yield stress. And then above that yield stress, there's a flowing state where you get a finite strain rate that depends upon the stress. In the physics department, we'd usually rotate this diagram by 90 degrees because we'd put this is the driving force and that's the response, but this is the way that's usually done in the plasticity literature.
Is that curvature on curving up or over the other?
It probably curves that way. I guess the reason that I didn't do it was that I wasn't absolutely sure. I should have probably done this like that. Okay.
Crucial at this point of real instability, or simply some range of lattice where this is
At finite temperature, it is exactly what you say. But this is just a zero temperature theory. Well, yeah, basically.
How does this depend on the R functions, the rate?
Look, you get into more formulas than I want to show you. There's a way back down at the bottom of this, where among the slides that I don't mean to show is a page with all of these equations on it for a very general version of the theory. If you want to, it's not hard. And in fact, some of the approximations are. So that was how matter stood until about a year and a half ago, maybe 2 years ago, when we discovered this paper by Johnson and Bill Johnson in this group, And what Johnson and company had done was they had, well, they were interested in making golf clubs and surgical equipment out of bulk metallic alloys. And therefore, they needed to know how to form these things. They'd figured out a way of making metallic glasses. They'd figured out a way by making a really complicated thing here to form bulk metallic glasses rather than just thin films of them. And that let them not only make money by producing interesting things, but it also meant that they needed to do some careful experiments in order to understand what the flow properties, the deformation properties of these materials would be. And so I don't have any nice pictures of just the thing unbroken, but here are the kinds of samples they were using. And here's Michael's picture again. And of course what they're doing here is they're doing it under compression, and they're forming a shear band, and eventually it breaks across there. But the interesting measurements look like this. Here's the stress that they apply, and here's the strain. It's not the strain rate. That's in fact what this picture is at various strain rates. And so they apply a stress. There's an offset here for clarity that they used, which you don't have to worry about. But basically what goes on is they start stressing it, and this is just elastic response. Then the material starts flowing plastically. At the higher strain rates, it goes through a maximum. Actually, in this case, it even rings a bit. And eventually finds its way into a steady state where it is straining at a steady strain rate with a fixed stress.
But is localization part of the process?
The thought is that in these things, it's not. Obviously, here it's broken. But it's an extremely important question is that both in we hope that the localization is not an essential part of this process, but it could be. And all that I can say is that we know from the molecular dynamics simulations that it doesn't necessarily happen, and that you can get into steady states of this kind. So, and it also works out from the theory. So that's what they're measuring is this steady state flow stress. What? This one, I didn't mark it. It's about 700 degrees, maybe lower. No, I think it's closer to 600. 640, I think, is the one. Here you can see there's a list of temperatures. And this is the most impressive diagram because look, here's about 5 or 6 decades of strain rate, which is unheard of and for other experiments, for any glassy material so far as I know. And this is that steady state, this is that flow stress as a function of strain rate. And so what you see is that at low strain rates, and especially at at high temperatures, this is just a line, and it's the Newtonian viscosity. It's viscous creep going on. But the important thing is that these curves bend over as you get to higher strain rates, and that was interpreted as entering a region of superplasticity. And then I think this is literally what happened. I looked at this graph and I said, well, look, that's exactly what has to come out without any detailed calculation of an STZ theory of the kind that we have. And here's the reason. Here's that picture that I showed you before, but also very interesting is that the colors change when you project it for one. All I've done is I've said, well, look, this is that zero temperature stress strain rate, if in fact I've got finite temperature, then I'm going to have thermally assisted creep in here. Okay? So there'll be some, maybe very small region at low temperatures at which this is going to come down to 0, and that basically is just a rounding of that curve. Okay? But it's going to level off and do something else as soon as I get up to in the neighborhood of the yield stress. And then even I can do this. I can plot that on a log-log plot in my head. And so this is not a numerical version. I just sort of drew it using the drawing facility of on PowerPoint. And you can see immediately I'm coming to take a log here. There's a finite stress. As I get closer to here, there are an awful lot of decades between here and 0. Okay? So I'm going to make a transition, and as it comes in here, it's going to think it's just leveling off at a yield stress, right? Because it looks as if it's going into that yield stress, so it's going to level off. But then it's going to come down, and it's going to go into this sort of Newtonian viscosity region. And so, look, the data was sitting in this kind of region. So the challenge then was to make a theory that would do this quantitatively and predictively. Mark?
Why you would expect the upturn later on?
Well, unless I have this going up, as a matter of fact, it doesn't come out of most of the versions of the theory that Michael and I invented. But what you expect is that when I'm in the flowing regime, that at least the strain rate should increase with increased stress. Right? And that's all this is saying. It should increase in some way.
Yeah, but I guess numerically for a million different glassy systems, it flattens out. It shows the same behavior, but it doesn't react.
Well, look, all I'm saying is that at very high stresses, it ought to somehow behave like a fluid.
Presumably appeals to the idea that the linear law on the
that's right.
used to apply at arbitrarily large stress.
Yeah, with maybe a different coefficient.
Yeah, and it may be before you get anywhere near to the upturn, the linear law.
That's right.
But if you plot the logarithm of a linear function, it doesn't.
Well,
yes,
but
because your linear function
there's
has a
two.
very different slope. You see at the beginning at low stress, you have one slope.
Yeah, so it's log is right. Yeah.
It's another slope.
But any slope 1 is going to have. Okay, well, none of the theories that I'm going to talk about have anything whatsoever to do with that region. Okay. And one of the things that I'm playing with these days is the version of those rate functions that will do something like that, because I certainly think that's what happens when you get to granular materials and maybe even emulsion. All right, another busy slide. So now I have to make a finite temperature version of the theory, and I'm underlining in red the things that are different, other than the fact that I'm going to have to make a temperature-dependent version of the rate functions too, but that's not hard. So what I'm going to do two things. One is that I'm going to say, well, gamma is only non-zero when I'm working the material, externally deforming it. What I need at finite temperatures is a spontaneous relaxation, an aging mechanism, if you like, that will happen. So I put in a factor, what I call rho of t, and that's going to be, this sort of super Arrhenius rate function for relaxation in glasses. And that's going to multiply. That's going to just change the annihilation and creation effect. The other thing I'm going to do here, and this is one of the several versions of the theory that we played with, but it's the one that I like best for a wide variety and growing variety of reasons, is that I'm going to say that I should characterize the internal state of the system not so much by the total number of defects in it, but by some sort of a measure of the disorder of the system, which should then predict the density of defects. And the natural way of describing the disorder in the system, I maintain, is by associating it with a temperature, an effective temperature, which is not necessarily, I'll say more about this in a second, the bath temperature, that reflects the fact that in a glass the internal configurational degrees of freedom can fall out of equilibrium with the bath temperature. So what I'm saying is that this is just detailed balance that's coming in here, but the detailed balance, instead of this being the usual sort of Boltzmann distribution, it's the Boltzmann distribution associated with the effective temperature, not the real temperature. So that's what's going to determine the balance between the rates of annihilation and creation of the STZs, and in fact what it's going to do is it's going to tell me that the total density of the STZs is going to have a Boltzmann factor associated with it, which but with the effective temperature replacing the real temperature. So the rho is the new thing, the effective temperature is there. I'm just normalizing energies to some sort of STZ formation energy, and what we need are two things now. We need a way to deduce what that function rho ought to be that sits there, and we need to then really think about the whole business of the effective temperature.
But where T is written in the first line,
that's real temperature.
That's
thermodynamic temperature, precisely.
It seems to be microscopic.
Which object? The STZ? Yeah, it should be microscopic.
Like the size of vacancy or 2 vacancies?
Or maybe 4 or 5 vacancies, but not more. Okay? And in fact, that's one of the other assumptions that's made throughout all this kind of thing, is that there's really only one kind of STZ, at least one kind that is associated with the shear deformation.
But are some macroscopic properties, let's say like Young modulus, depend on lambda and delta, those densities?
To a first approximation, which is by far as much as I'm going to go, the macroscopic moduli are independent of that. Now, if you talk to the folks, Craig Maloney or Ed Lemaitre, or perhaps they will tell you that the state of disorder will also affect the moduli. And that may be very important, but for the moment I'm going to ignore that. Okay, I'm going to assume that the bulk modulus, that I have a sufficiently low density of these defects, and that the bulk modulus is whatever it is associated with, for a system without any or many of such defects. Okay? Yeah. But a very slow fluctuation. As soon as I'm in the glassy region, where I'm basically I've dropped out of the ergodic regime, and where the rearrangements are extremely slow in the system, then I can still think of the STZ as being formed spontaneously or annihilated spontaneously. But I should think of that as being a very slow process. So anything where you see that rho sitting there is something, it's a small rate. That's a very good question, and I think the answer is yes. In fact, in my paper on this subject, I actually wrote down how that works and how you can get a sense of how this thing is going to behave. But I didn't even include that slide in this. Yeah. Well, that's right. That's right. But a system very far from equilibrium, but not changing very rapidly. That's a very good question. It's a very good point. And we can talk about it later, because it's a tricky business how you use fluctuation dissipation theorem in this system. Yeah.
First time this kind of a general relation of voltage with state was proposed in Russia in the middle of
Yes.
by Jan Kulic for
But-
plasma. By Jan Kulic
yeah.
plasma. And after maybe 30 years it was rediscovered by
Yeah.
$10 trillion.
Yeah. 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 But Leticia Curandola has done very interesting things, and I think she's also interested in knowing who did it earlier. All right. Here's how you calculate what rho is, and this is already interesting. Here's the viscosity, sort of linear viscosity, Newtonian viscosity for this metallic alloy as measured over, 600 or 700 degrees and 600 degrees in temperature, but something like 15 orders of magnitude in viscosity. And basically, the idea is to fit this the formula that comes out of the theory that I was showing you says that viscosity has the form of that yield stress divided by this quantity rho, and then there's this Arrhenius kind of activation factor. So with this, you can fit this data and just figure out what rho has to be. And so we've done this in several different versions, and it's got interesting aspects, but it's not very hard.
Is there a fundamental explanation of a form like that?
Well, I tried to hint at it here. I think that the plastic strain rate is going to be some. I'm sorry. I didn't. That's what comes out of grinding turning the crank on the equations. It sort of looks reasonable, but it's going to be proportional to the stress of those stresses. But you've got to work your way through it, and basically it's.
I meant specifically the Vogel-Fokker.
Oh, that's purely phenomenological. Okay, I'm just all I'm trying to do is to relate this to something that some people in the audience may be familiar with. But that seems to fit a lot of the data. In fact, what you even may notice here is that they fit this data not to Vogel-Fulcher but to Cohen-Grest, and I've used that fit on occasion too. But I would say a few more words about effective temperature. The basic idea is that when I deform a material, I force atomic rearrangements to occur. In a certain sense, I'm stirring it. Okay, and so that I can think that what I'm doing is I'm driving these configurational degrees of freedom, the arrangements of the atoms themselves, not so much their little vibrations, but their organization within the material, out of thermodynamic equilibrium, and in a way that, of course, is going to be very slow to relax back. The term inherent states I find very useful here. That there are, even in ordinary liquids, if I just take all the kinetic energy out, the atoms will have some sort of intrinsic organization, and then the question is how they move from one such state to another is important. Now, I don't know how to describe that state of disorder, but that all by itself is an important statement. When we really have no knowledge of anything, what we always do is we say, well, we have to figure out what the most probable state is. And so you figure out what the most probable state is, what the state of highest entropy is given certain constraints like constant energy, and that you immediately think then that you ought to describe the system by a temperature. And maximize the configurational entropy and figure out what the derivative of that is with respect to the energy, and I get a temperature. And then I would say, well, the STZ fluctuations, almost by definition, have to be something out in the wings of this disordered distribution of states. And therefore, the density of STZ should be proportional to this Boltzmann factor, what I was saying before, where it's the effective temperature that sits there, not the real temperature. That is appearing to be a increasingly powerful concept. Here's Mike's pictures again. He, again, is seeing, he pulls on this thing and he gets something that looks like a shear band going. That's the STZ activity. Here he's looked at the dilation and contraction, dilation in blue and contraction in red. And you might think that you have a little bit more dilation than contraction within this shear band, but you have both in very roughly speaking equal amounts. That basically the point that I want to make here is that what's happening in this shear place where the shearing is larger is that I'm disordering it. I'm making it frothier. I'm having both low density and high density fluctuations that occur in there, and therefore I'm going to assume that I have a higher density of STZs in there. Or, and what I really like to do, as I've said on the previous slide, I'm going to say that that's hotter, but effectively hotter. Not hotter thermodynamically, but hotter in the effective disorder temperature that sits there. And there's a clue, by the way, of something that I'm not going to get a chance to say anything about, is that what we can say is that the shear banding instability is going to happen when I have some fluctuation that makes it hotter effectively in a region like this, and therefore it's going to be easier to flow. And the usual explanation for why that sort of explanation doesn't work is that if you talk about real temperature, ordinary temperature, it diffuses out at a time much shorter than any time of any interest. But this effective temperature is going to diffuse extremely slowly. It really requires these activated rearrangements of the atoms to make it happen. And therefore, that old-fashioned idea is almost right, that you have to use the effective temperature in there. Well, look, I wanted to show very briefly, this is Doug Durian's numerical simulation of a sheared foam, and the numerical analysis of that, where they measured, this is Ono, Hearn, Durian, somebody related to me there, Andrea Liu, Sid Nagel and company. I find this a very important paper. That they measured the effective temperature, the actual temperature, because the foam, of course, has no real temperature at all, but they measured the temperature by computing various sorts of fluctuation coefficients and using Stokes-Einstein, among other things. And they got something that's quite consistent, that this is now they're computing the shear rate, and the temperature is a function of shear rate, and it seems to level off at low shear rate, not go to zero. So what this is saying is that if I have something where the real temperature isn't very important, and I start shearing it, if I go very slowly, I just have to go for a longer time, I get to something which is some universal quantity related to that kind of material, which Andrea Liu thinks is something like the glass temperature. And that's sort of the kind of order of magnitude of stuff that you get out of it. And that's an important feature of this effective temperature. It tells me how to write an equation of motion for it, which I think is on the next slide. Yeah. So here's the equation of motion that I've written down. And the first term is precisely that. Here's our familiar gamma, which is the rate at which I'm dissipating mechanical energy. And I'm saying that that's what's driving this effective temperature, but it drives it so that it approaches this chi infinity. So that if rho is 0, in other words, the temperature is very low, this term cancels out. And this is simply saying that I shear it for long enough, the system gets some sort of equilibrium stirring or equilibrium frothiness. And so that's the first term in this. Basically, this is an energy balance equation. And then the second term tells me about how this effective temperature relaxes towards the ambient temperature of the bath. And now I have to say, well, there's this basic relaxation rate that's sitting in there. And I've played around a little bit with the question of whether this density of STZs, this is the density of STZs for sure that belongs there. But whether it's the STZs or some other density, and that's a parameter, and let's not get into that one for this talk. It's easiest just to say beta is 1. But incidentally now, basically, apart from a parameter that sets a time scale for the whole thing and matching to experimental data, the only free parameter I've got in this theory is this quantity kappa. And it turns out that kappa is equal to 2 that fits the metallic glass data very well. And so I'm not in a situation where I've got a huge number of parameters and I can fit an elephant. I've got basically one parameter to deal with, but I'm not fitting very much. But here's the graph now of this is the experimental data that I showed you before, and here are the theoretical curves, and the theoretical curves. The only reason for the dotted lines is that Bill Johnson admitted that they didn't have very good temperature control and suggested that I should fudge the temperatures. You can do it another way and just sort of get the parameters directly from their measured Newtonian viscosities, which is what Michael and Leonid and I did in the first paper we wrote on this. So you can get pretty.
Can I ask, what would they call the glass transition temperature?
I don't know. Look, the glass transition temperature is a very poorly defined thing. The people say, okay, it's when the viscosity gets to 10 to the 18. But independent of what material you're talking about.
The slope of the stress strain curve, which is linear, it's not obvious to me that for this data.
Well, this is strain rate, by the way. This is not. Okay, so this is where that slope. Well, the viscosity, the slope is just because you assume that it's linear, and then the magnitude of where this thing is the
viscosity is.
Yeah. Well, I think of viscosity as like equivalent of creep in this kind of thing. Okay. Yeah. The generation of yeah. Yeah. I'm not sure. You have to tell me in more detail what you mean on that. Because it does not sound quite right, but I'm not at all sure. And then, here's the experimental picture I showed you before. Here's how the theory looks on this, and a little bit of a cheat here because I don't have a good equivalent picture of that with the effective temperature theory. So I put the slightly older version of our Falk, Pechenik, and me theory there. But basically, the answer is you can you get qualitatively and even quantitatively the same thing.
On the left graph, actually, I saw the experiments. The leftmost curve corresponds to brittle deformation, where you actually have localization. But on the left,
Yeah.
You have a dashed line.
Well, look, what I'm guessing is that if I did the calculation instead of assuming that I have a completely uniform and forcing uniformity on it, if I did it on a sample where I allowed some kind of shear banding or localization of the stress or the strain to occur, that it would go on have some sort of instability there. But that's that's completely arbitrary. I don't know. We haven't done that yet.
That's kind of my question. It seems to me that all the results you showed so far do not account actually for localization and brittle.
Yeah.
Is this correct?
I'm sorry.
I'm saying it seems to me, I jump to this because it seems to me that the results that you discussed so far are okay for distributed deformation.
That's right.
But they do not account for brittle deformation with localization.
They don't. That's right. They do not account for any kind of localization, and that's something that we're working on. I guess Anthony isn't here.
The theory, does it predict that homogeneous deformation is stable if you do just a linearized perturbation on it?
Well, look, if you just do the theory with this parameter beta equals 1, it predicts that you have bulk stability. It does not, however, and this is another interesting question that we're trying to look at, it does not tell you anything about the stability if you have a free surface, okay, which could very well be where the origin of shear banding is. If I let beta, that number beta, be less than 1, which tells me that all the regions that contribute to the thermalization are somewhat more populous than the STZs that contribute to the shear banding, then I have a situation, I could have talked about this too, where I predict a region of instability against shear banding. And it's very interesting. At non-zero temperatures, you have a region of shear rates. And you have to get up a band. Within that band, it has to be above a certain amount, but below another amount, at which the instability kicks in. It makes some interesting predictions, which I'm just not ready to vouch for at the moment. It's just something to be thinking more about.
But when you do have a shear band, should you regard that? I mean, does the picture of isolated STZs then go away if you have large?
No, you just say that in this version of the theory, you say simply that you have a region that's heating up, and therefore there's effectively it's disordering. Therefore, you have more STZs. Therefore, you have a stronger flow. But you can. There's another. Again, I published a paper 4 or 5 years ago now that I keep telling people I wish would go away, where I actually looked to see what would happen if I said that, well, one STZ makes a change in the stressor in its environment and therefore triggers or makes it more likely that the neighboring STZs in this direction or that direction will transform. And you can get shear banding out of that too. Although I don't like the kind of shear banding. The whole theory is missing some important length scale.
There's no energy transport associated with your effective temperature when it has gradients.
Very, very slow.
So slow that...
So slow that it's irrelevant for this stuff. But not so slow that... The point is that that's what does produce an interesting length scale in the problem. If you put it, because you can estimate using Stokes-Einstein, you can estimate what the diffusion coefficient for the effective temperature ought to be. It turns out to be enormously small and gives you a perfectly reasonable answer for, say, the the thickness of the boundary between flowing and jammed regions in the material, which is what it's supposed to do. What actually determines the width of an actual shear band, I don't know. I strongly suspect that that has to do with the instability coupling with the surface.
If you look at the theory, you have this gamma, which was an average of dissipation over the entire volume. And that would have to become some local.
That's right. Well, everything in the.
And there'd be some natural length scale that would have to appear in that average.
Well, not necessarily. All I'm doing here is I'm saying that all of these internal state variables, the gamma and the delta and the lambda, are functions of position, and I'm obviously implicitly assuming that they're sort of coarse-grained over a length scale over many STZs. Yeah. But I don't think there's a problem in that.
If the system went unstable, it might be.
That's you might generate smaller length scales, and then you have to worry. But look, we take things one problem at a time. Right?
There does seem to be a good experiment that tests one of these ideas of localization, whether you need a free surface, Hertzian indentation of a sphere that makes the deviatory stresses greatest beneath the surface. So you would, if you can nucleate subsurface in that case, that would be a hint that maybe you need a mechanism that doesn't appeal to you.
Michael, do you have any insight on that? Because you've done a numerical experiment on precisely that.
Would it be different for plane strain with a cylindrical indenture, or would it?
I simply don't know. I've not looked.
The maximum deviatory stress is still subsurface, but the instead of being a third, it's 0.5 or something like that.
That's so we do see nucleation in the MD simulations. We see nucleation of shear bands beneath the indenture in the case for cylindrical 2D simulation. So.
Rather than surface nucleation.
Rather than we'll have to look at it.
Yeah, let's look at that. It's a good point. Yeah.
I want to look at it more carefully.
I'm going to have to round up because I know. Do you want me to take another minute and talk? Just to give you a brief remark about the latest ideas on. People can leave. This is stuff that the question was, well, okay, we have this STZ picture. There's this rate factor that I call rho that's sitting all over the place, and how does that does that give me any hint about how to figure out what the rho temperature dependence of rho really ought to be? So I couldn't resist thinking about it a little bit. I didn't realize how I did sort of, but not enough. Realize that I was getting into an age-old field, and there are a zillion theories of super Arrhenius, Vogel-Fulcher, ways of getting that kind of behavior out. And what's even worse, fierce loyalties to one position or another, and sensitivities to whether you. But yeah, it's a religious field. So I'm being very careful. I'm sending my latest preprint out only to a few selected friends, and Swagatam will tell you we're discussing intensely, whether this makes sense. But the idea was simply this: that look, if I want to think about the thermally activated formation of an STZ, which is presumably some sort of density fluctuation. It's a little bit like a vacancy or a region with a little bit lower density, and then if I'm going to form it spontaneously, there's got to be another region next to it that has an interstitial or a higher density. And of course, the most likely thing to happen if a thermal fluctuation actually does that is that it's just going to go right back. So the question is, well, how can I stabilize some sort of a fluctuation of that kind? And then the idea that came to my head after having looked at a paper by Sharon Glotzer who were doing molecular dynamics of glass-forming liquids, and was looking to see how a glass-forming liquid at below enough temperature actually makes a transition from one inherent state to another, and she finds that one atom sort of pushes its neighbor, and that pushes its neighbor, and those kinds of things happen. So I thought that, well, maybe what's going on is that there's some chain of slightly loose atoms along which these two things can somehow drift apart, and that's a thermal fluctuation. The other kind of picture that you may think about here is that we know in granular materials there are these force chains, that the stresses are transmitted along essentially one-dimensional structures. So the question was, okay, if that's what's going on, I ought to be able to predict the probability, the rate of formation of such a chain, and see whether that will give me anything that looks like a Vogel-Fulcher, Cohen-Grest, super Arrhenius kind of behavior. And the reason that you think that might happen is obviously I've got to spend energy to make each link in that chain, but as the chain gets longer and longer, it has many more configurations that it can adopt, and therefore there will be what you might call an entropic contribution. And now it makes me feel old because I'm really going back to papers that I wrote in the 1960s about what's now called instantons and stuff like that, and thinking about how you calculate these sort of activated processes in systems that have many, many degrees of freedom. So I did a back-of-the-envelope calculation. At first it turned out completely wrong, and you don't want to go into the theory of this, but you sort of, here's what's the probability of forming that chain. It has a whole bunch of factors in it, and obviously I want to say that there's a Boltzmann factor for each link in the chain. The chain has n links and it spans a distance r. There's some number of choices that it can go in each point. So I'll put q to the n in there. And this is now borrowed from the Fleury polymer picture. Well, how many chains will reach a distance r if they have length n? And that's just a plain old diffusion factor that sits there, or like a random walk. And that's in fact what I think Anel Lemaitre and I did wrong the first time, was we based everything on that. Let's go here. I know that the chain, these excitations, I can't have two of them at exactly the same place, pushing atoms in different directions. So there has to be some sort of a self-exclusion effect. So there's some energy of self-exclusion, which you do a la Fleury. And then the interesting and the latest wrinkle in the whole business is that this chain actually has to appear in a random material, disordered material. The glass is intrinsically disordered. And therefore, there should be a localization effect that looks like that. Whether it really always looks like that with this exponential or not, I don't know for sure yet. It certainly is true in certain cases. And what's particularly interesting then is that I can calculate the strength of that disorder, because this is the ratio. The ratio. The disorder is characterized by the effective temperature. But this is an activation energy, so that in fact gamma turns out to be proportional to the ratio of the effective temperature to the real temperature squared, which means that at low temperatures this gets big. Again, that's what you would think, is that you go to lower temperatures, thermal activation is small, and therefore a diffuser in this random potential thinks that the potential is steeper and trapping him more strongly. And so they put all this stuff together, actually neglect that because it's negligible for large chains. And basically it's a back of the envelope calculation. You just calculate what chain is long enough, so that I start gaining more in entropy than I'm losing in energy if I make it longer. But again, it's the nucleation problem. And out on the back of the envelope pops the Volcker formula. Now, it's a little bit more complicated because it's also got this rather strong temperature dependence sitting there. But you can then compare this with the measured, for example, this is orthotorphenyl, one of the structural glasses that's best studied, and you can measure its viscosity, and then you convert that to an effective activation energy, which is at high temperatures is just a constant, so that's the Arrhenius behavior, and then it comes up, and with not too many fitting parameters, I guess 2. I can make it that formula go right through the data, and I can do something similar for the metallic glass, and there isn't quite as much data for that, but that's the same data as that viscosity picture that I showed you, and it seems to work. Now, where we go from this, I don't know, but I like the picture a lot better than some of the sort of hand-waving stuff that some of my very good friends have published in the literature. I think that's. I better stop there.